Hello, everyone. Thanks for coming. So today in my talk, I'm going to be talking, as Steve mentioned, about exploit mitigations on Windows. Something I'm coining, pun fully intended, nickel and dime exploit mitigations. Effectively, these may be some of the smaller mitigations that are built into the OS, aren't part of really any release notes, but affect the cost of exploitation. So we'll go through what those are and have some demos as well. With that, I'll go ahead and get into it. So as Steve mentioned, my name is Connor. I work at CrowdStrike on the Windows sensor, and pretty much I just like anything related to Windows internals, low-level code, C, C++, etc. So as the title infers, I'm talking about something called nickel and dime exploit mitigation. So this is a poor analogy, but at my home, we have a spare change jar. So cash, those paper bills that aren't used anymore. You get change back. You get these nickels and dimes by themselves. Can't really do much with that. So you have like a big 5-gallon bucket and you just store them in there. And then eventually over time, you have something worth quite a bit. These are what nickel and dime exploit mitigations are, in my estimation. So there's some of the smaller mitigations that we may not take a look at, take for granted, and they may not do a lot by themselves. Some of these mitigations, they're more defense in-depth mitigations where if they were the only mitigation on the box, that doesn't do much for us. But when you put them together on top of what's there, they can significantly raise the cost of exploitation. But before I talk about that, let's get into effectively how we got here, why Microsoft is choosing to continue to address things with mitigations. Exploit mitigations, they've been around for a very long time. DEP, ASLR, I'm not going to talk about that because there's a dime a dozen white papers on those mitigations. You also have control flow integrity. And these mitigations really address stack overflow and use after free vulnerabilities, which historically, as exploitation grew, these were some of the more notorious vulnerability classes. So buffer overflows and use after freeze, if you want code execution, they require executable memory, which is what DEP allegedly mitigates. But in order to get around DEP, using some code reuse techniques, well, you need to know the layout of memory, the address space. Well, if you're relying on exploitation with both of those things, ASLR and DEP combined kind of address that. And in the case of use after freeze, you have a freed object in memory usually. C++ objects, they have a virtual function table, a bunch of virtual functions associated with them. Well, what if you as an attacker could insert some memory into that freed slot, put your own function in that function pointer table, and try to get the OS to invoke that? That would not be good, and that's what control flow integrity does. And Microsoft tells us that as of 2016 at Black Hat, stack corruption and use after free vulnerabilities, they have significantly gone down. Dave Weston and Matt Miller did a talk. This is a graph from their slides about what exploit vulnerability classes are being targeted in the wild. So as of 2016, as I mentioned, stack corruption and use after freeze, they've gone down essentially. Well, this success with DEP and ASLR control flow integrity, that was an indication, hey, maybe we should more heavily invest in the exploit mitigation space. And this led to many of the more modern mitigations, which I won't go over all of those in depth, but effectively, all of these mitigations together, they either prevent an attacker from hijacking control flow, so forcing the program to execute code in another region that an attacker controls, or create executable code, because even if we can hijack control flow, well, we need to execute some code somehow. These together in user mode and kernel mode effectively do that. But we know that exploitation is still occurring, obviously. So why is this? Number one, the mitigations, they could just be disabled by default. This is the case that we see, actually. There's some issues with, for example, Arbitrary Code Guard. If you're saying memory can only be writable and executable, but never both, every time you open a browser and it does just-in-time compilation, you're constantly creating read, write, execute memory, or memory that's being modified. That violates Arbitrary Code Guard. So there's a lot of compatibility concerns. But there's also other issues that need to be addressed outside of hijacking control flow and creating executable memory. One are documented features that the OS will generically leak you kernel memory from user mode, as an example. ASLR. It's not fully implemented in kernel mode in some very specific cases. We have data-only corruption. What if we don't even want to create executable memory? What if we just want to corrupt some data structure that does something interesting that the OS gets tricked into believing maybe it's a privileged object instead of an unprivileged object? And other techniques such as that don't rely on control flow hijacking. So many of these smaller mitigations, they address these concerns, and that's effectively what we're going to be talking about today. The first one is implementing ASLR fully in kernel mode. This is probably the oldest of the mitigations I'm going to talk about. I think in 2016, this was implemented. But effectively on Windows, with the implementation of virtual memory, we have these things called page tables. And they effectively map virtual memory to physical memory, like RAM, for instance, frames. And not only that, physical memory by default, it doesn't have permissions, right? When you install RAM, there's nothing really that says out of the gate, hey, when this memory region boots up, it's readable, it's writable. Virtual memory kind of is an abstraction of that, and it also enforces those permissions. Well, page tables reside in physical memory. If the CPU can only access virtual memory while operating, and we need to somehow update the page tables to say, hey, someone did a virtual protect operation. This memory is now writable instead of readable. Well, if the CPU can only interact with virtual memory and the page tables are in physical memory, that's an issue. So what happens is the OS maps the page tables into virtual memory in the form of this array, effectively. Well, this array is needed pretty early in the OS loading process. So what Microsoft did is they put it at a static address across all OS implementations. On 64-bit, it's located at f extended 68000 for the page table entries. This is an issue. Why is it an issue? Well, an adversary, if you use virtual alloc or something to allocate some memory, the OS is going to tell you where that memory is located at. If you can always know where your memory is at and the page tables are not randomized, well, you can effectively just index that array to know where your page table entry is that corresponds to your shellcode page, for instance. And if you know where that is, well, if you have a write primitive, what could you do? You could corrupt the metadata of the page table entry to effectively say, hey, this page is now executable instead of writable. And effectively, that's the formula you would go through. You would obtain something called the virtual page number, which is essentially like a frame number in physical memory, and then do some calculations based on whatever architecture you're on and index the array itself. This is actually mitigated now on more modern operating systems. As we can see in this screenshot here below, there's a function called mi-get-pte-address, which performs this same computation with compiler optimizations. So now what happens, this is a screenshot from WinBag. Effectively, this PTE base represents the page table array that's now randomized. And as we can see, using the same formula, if we use the PTE extension, we can see that the frame on the screen corresponds to the same frame we extract from the PTE itself. Effectively saying we can use the same formula, but now we need a read primitive because that memory is randomized. We don't get it for free just by nature of us being on a 64-bit system, for instance. So that's another example that was the first example of ASLR being fully implemented. There were still some addresses that were not fully randomized. Another specific place where they did this, and this is just recent in the insider preview builds, is this structure called K-user shared data. And what this is, it's a shared structure in the OS that manages a lot of interesting information, even things like the system time. Same thing here. This was located at a static address historically on Windows. And it's a writable piece of memory for attackers to use. So an attacker only needs a write primitive at this point. So let's think about this from the perspective of a remote attacker. A remote attacker is somehow able to write into kernel memory, but you're a remote attacker. You don't have native code execution on the machine, so you don't know the layout of memory. Well, if you need a place to store your shellcode, K-user shared data is a wonderful place to do that. It's writable, And most memory operations on Windows are page aligned. So in this case, the K-user shared data structure is only hex 700 bytes. Well, if a page is hex 1000 bytes, what does that leave? About 300 bytes of uninitialized memory where an attacker can just place shellcode. As we can see in the screenshots here, once you get to an offset of hex 720 on this version of Windows, you have a writable place of memory that's not used by the OS. This says read-only mapping. That's a typo by me. It should say writable mapping. But in the latest insider preview builds, this has been mitigated. And what's happened is Microsoft, instead of randomizing the address, which would be an interesting engineering feat, what they did was they created a new mapping. A mapping essentially is another virtual memory address that's different from K-user shared data, the historical address, but they're backed by the same physical memory. So what that means is, let's say you do a write operation to the writable version of K-user shared data. Well, that will get reflected also in the read-only version of K-user shared data. So now what happens is anytime the system needs to do something like update the system time, we go through the writable symbol called writable shared user data, and that gets reflected in the read-only page. And by doing this, an attacker can no longer just arbitrarily write shellcode to FFFF 780 all the way through sign extended, right? They need to now know where K-user shared data, the writable version is. And why this matters is because this is kind of defense in depth, because if the page tables aren't randomized, well, even though you have a writable, if K-user shared data is not randomized, well, and the page tables are also not randomized, across all systems, you know the page table entry address of K-user shared data because they're both not randomized. So you know that, hey, my shellcode will always be at this address. Well, the page tables aren't randomized as well, so we can just index the array for that, and it's synonymous across all systems. So now we're going to talk about something I'm referring to as restricted caller improvements. So on Windows, since 8.1, there has been a function known as xIsRestrictedCaller. You may or may not know that by default on Windows, you can use APIs like NT-query system information in order to actually get kernel addresses from the kernel into user mode from a default process. That may seem kind of foreign, like why is that allowed? But it's for historical reasons and for systems administrators. Well, now what xIsRestrictedCaller has done since Windows 8.1, it says effectively special processes like browsers, for instance, or highly targeted applications that are sandbox are not allowed to make those API calls. So you're not allowed to leak those kernel addresses into user mode. Well, now what happens is this function, it builds on top of that. So if you open up cmd.exe and you run a program by default that calls NT-query system information, as of today, you could get kernel addresses into user mode. That's obviously not a good thing from an attacking and defensive perspective. Well, good for attackers, I should say. Now we build on top of that. We say, hey, if you want kernel addresses into user mode, you effectively need to be an admin now. And what they actually do is they check if your process has the SE debug privilege enabled. And what that does is an admin should theoretically be the only type of process to get that privilege into your process. So since Microsoft doesn't recognize an admin to kernel security boundary, they effectively say this is mitigated, because if you're trying to leak kernel addresses, well, you already need to be an admin. If you're already an admin, you've effectively escalated privileges already. So how does this actually look? Well, you call NT-query system information from user mode. Eventually, it takes a code path into kernel mode. And there's various classes that you can pass in to get different information. One of the most popular is the handle information. And what happens is when you use that class, xIsRestrictedCaller, it says, I see you're not a low integrity in process, so go ahead, keep on doing execution. But then it gets to a point where you verify as well, should we disallow kernel addresses to medium integrity processes? And so the OS now can restrict kernel addresses or strip them from being returned into user mode. How does this work? Well, when the NT call OBP capture handle information occurs, the default kernel address returned into user mode is null, 0. And only if kernel addresses are allowed should this be returned to the caller. So either if the feature is disabled or if you have debug privilege. Why should we care about this? Well, there's various exploit techniques in kernel mode. One of them is hot swapping a process token. So you have something called the system process on Windows. It's a privileged process. Most of the kernel threads execute there. Well, it has a token to effectively say, hey, this process has these privileges. Well, an attacker that can access kernel mode memory can say, hey, let me locate the process object associated with system process. Then let me locate my process object, and I'm going to hot swap the token from the privileged process over my current process. Well, your unprivileged process now inherits the privileges afforded to the system process. Well, in order to do that, you need to know where the process objects are. And NT-query system information gives you that by default, or not by default, but through those classes that we talked about. So effectively now, if you even want to do that exploit chain, you need to be an admin or have debug privilege in your process. And if Microsoft doesn't recognize an admin to kernel security boundary, that means, well, if you're an admin and you can get kernel addresses, that's not really a concern because you already need to be an admin. And this leads into another mitigation. Effectively, I'm just calling previous mode corruption mitigation. So this is also an insider preview. It's fairly new. And effectively, it comes back to this previous mode field in a K-thread object, which is effectively the kernel's representation of a thread. It's how it manages it. And previous mode, it can either be one of two values from this enum. It could be 0, which is kernel mode, or user mode, which is 1. And this lets the OS know when it's operating, let's say, on a syscall that's being dispatched. Hey, this caller originates from either user mode or kernel mode. System call is a very complex mechanism because you're taking user mode provided parameters and you're copying them down into the kernel to try to, get some memory back for the caller, or open up a handle or do some other kind of action that the OS needs to interact on your behalf for. Why is this important? As I mentioned, it's used in a variety of security checks. So an example of this is when you call NT terminate process. When you call the terminate process API, you pass in a process handle of the process you'd like to terminate. That process object lookup involves the previous mode field from K-thread. So what happens is when you pass in the handle, we need to look up where that handle is. And one of the NT calls that happens is this reference object by handle with tag. And the previous mode is included in a argument there. Well, handles are stored in a per process handle table. So what happens here in the checks outlined in the screenshot is the kernel handle, I should say first, a handle is effectively just, it would seem like an abstract value. It's something like maybe A8 or some hex value that's 2 or 3 digits long, effectively. And that is an index into this handle table, effectively. Well, kernel handles are stored in the system process handle table. Kernel handles are any of the handles opened up by kernel mode component. They're privileged. So they have a special sign extension on them with FFE. And what happens is when we try to look up the object associated with the handle that we want to terminate, in this case, a process, the OS checks, well, is this in the kernel handle range? And if previous mode is set to user mode, what does that say? It says effectively a user mode caller is trying to access a kernel mode handle. Well, that's sketchy. We don't want user mode clients to have access to these kernel mode objects. And a status access denied is returned. That's not the mitigation. That's a current implementation of what previous mode would be used for. So what you can actually do as an attacker, and it's well documented, fairly old, is with a kernel primitive, you can locate your own K-thread object or any arbitrary K-thread object using either a memory leak or some kernel address space layout randomization bypass, or calling NT-query system information, which we mentioned earlier. Once you get that, previous mode is located at a fixed offset in that structure. Well, you can decrement your previous mode because by default, we're user mode clients, so our previous mode is set to user mode. You can decrement it to kernel mode, and then you dispatch a system call. Well, the way that the system call works is a trap frame is created and the information surrounding the call is captured in that trap frame. And what happens is whatever the previous mode was at the time gets captured in that frame and passed to kernel mode. And there's no additional verification because user mode clients should not be able to access kernel mode memory. And we're using a vulnerability to do that in this case. Well, now I can make system calls, and every time previous mode is checked, it says kernel mode now, even though I'm a user mode caller, and I can do privileged actions such as accessing privileged objects, reading and writing into kernel memory, or other type things. Well, with the latest insider preview builds, this is no longer the case. So what happens is every time a system call is dispatched from user mode, KI system service obtains the thread, which is located at that GS segment register at offset 188 before that outlined red screenshot. And then at offset 232, which is previous mode, it's explicitly set to 1 now. So even if you corrupt previous mode, then dispatch the system call, the OS effectively says, I'm not going to trust that. I'm always going to set you to user mode. So this mitigates that first issue. Then as part of defense in depth, there's technically a way you could win a race condition maybe, where you have another thread that's editing the previous mode or trying to, and do it in such a way where after the previous mode is set by the OS, you're still able to change the previous mode back to kernel mode. Well, upon sysret, when the execution returns into user mode, previous mode is also verified again. So not only if you're able to somehow corrupt previous mode at the time of dispatching the call, you have to make sure that you restore it before you return into user mode. And if you don't, a new bug check code called previous mode mismatch is emitted and you get a blue screen. So let's take a look at, we've talked about these mitigations. Why would Microsoft address this? What's the point of doing these smaller mitigations that seem, very niche? What's the effort here? Well, a practical example would be in an exploit where you have local execution and you don't have any type of ASLR bypass but you have a kernel mode write primitive, for instance. Well, you have an easy way to always get a read primitive as well. What you would do is locate the kthread object of a thread that you control, corrupt previous mode to 0, and then effectively call the nt-read virtual memory API. Normally what would happen, since previous mode is set to user mode, is it would say, hey, if you're trying to access kernel memory, status access denied, you're not allowed to do that. Well, if you can corrupt previous mode and call nt-write or nt-read virtual memory, you can read and write into kernel memory from user mode. So here's an example in C of how you would go about using nt-query system information to locate an arbitrary thread object using the process ID of the target process as well as the handle itself. And then I have a demo. I'll kind of explain it first because it goes quickly. On the top, I have a command prompt that's running as admin. And on the bottom, I have one that's not running as admin, excuse me. Or flip that. Top one is unprivileged. So in this case, trying to run a test binary that tries to use this primitive in order to leak the kthread object so I can corrupt it. Well, it's 0 because I don't have the privileges. I don't have debug privilege. And then if I try to enable debug privilege, I get an error because I'm not an admin. I shouldn't be able to enable debug privilege. But previously that would have worked and there would have been a kthread object there. And then even as admin, by default, I don't have debug privilege. So I don't get a kthread object. It's only until I enable debug privilege that I get that actual kernel address there. So now from an arbitrary perspective, there's no generic way without some type of vulnerability specifically for the nt-query system information, in that case, handle creation using that undocumented class to leak a kthread object. So let's say that you do have some kind of leak or some kind of kernel address space layout randomization bypass. In this case, I'll use a pool overflow to kind of outline this in an intentionally vulnerable driver. Well, when you try to go to corrupt previous mode and dispatch a system call to try to access some privileged object or read and write into kernel memory, it's effectively impossible. So there's a third switch here called use memory disclosure vuln. And when the binary executes, we can see that we get the kthread object using the vulnerability. And then I have a get char here that says, we're about to corrupt previous mode. If you do this, you're going to get a blue screen. And in WinBag, we come back here and we see that there's a blue screen. And using analyze, the actual status code here is previous mode mismatch. And if we look at the stack, the way that this driver vulnerability manifests itself is through an ioctl. And so that requires a system call. Well, the previous mode was corrupted at the time the system call was issued. And when we return, it's still kernel mode. The OS says, hey, why does a user mode thread effectively have a kernel mode previous mode? And a blue screen occurs. So what's the takeaway here? Not every effective mitigation has to be a large one. Some of those mitigations that we saw in the beginning of the talk that were outlined in yellow, those were huge investments that took a lot of time, a lot of research, a lot of threat modeling. They came with blog posts, demos, and their documented features, right? Not everything has to be like that in order to move the progress bar forward. Many of these mitigations you may not even be aware exist in the OS. So that's where you can take advantage of things like Insider Preview, which are not features that are fully implemented in the prod versions of Windows, but maybe some things that are upcoming. And you also have the SDK that you can use. And these may outline trends that Microsoft are onto, or just other interesting changes for the future. And even some of the smaller mitigations have the potential, depending on your primitives, to increase exploitation costs. In that case, if you have a vulnerability that's only a decrement primitive, that's all you have nothing else. Well, the previous mode technique was a tried and true method of turning just a decrement into an arbitrary read-write primitive. Well, that's no longer the case using that generic technique. So it has increased the cost of exploitation. And it's always happy exploit writing. Here are some references. And with that, I will take questions. And again, thanks for coming to my talk.
All right, a very technical talk, awesome stuff. Got a few questions DM'd to me, and I saw some in the chat as well. So I'll start off with this one. Why are techniques like specifically token stealing still possible? It seems like something easy to protect where someone could bind PID4's token to the eProcess address or similar. Why aren't they fixing that?
Yeah, well, eProcess to begin with, the process objects themselves are writable. So the issue with that is we have to remember there's a development issue where, like Kaiser shared data, for instance, the system time is literally updated every second or whatever it is. So there's development concerns where if you try to do something like that, let's say make it read only or do some other thing, there's issues that can arise there. And it's not as easy effectively as just saying, well, hey, let's mitigate this. There's good ideas, but it's something slowly but surely because it's an undocumented structure as well. So that's what I would say.
Yeah, this is a big question here that I often get a lot as well, which is, do you think that the mitigations on Windows have gotten to the point where very soon, if not already, exploitation won't be possible? Or do you think there'll still be one-offs?
Yeah, I don't think it's going to be impossible, at least for the upcoming future. It's definitely harder, I would say. Not that I'm an expert by any means, but it's more difficult. But there are still blogs that come out all the time about exploits that are occurring. There's untapped attack surface areas. There's some techniques, for instance, that Microsoft may say, we acknowledge this and we may not try to mitigate it. So there's always going to be researchers that find things. It's definitely harder. The bar of entry, I guess you would say, is more difficult, but I don't think it's cause for concern, at least right now at the current moment, but it's just my opinion.
Hi, Connor. What are some of the tips you would suggest for detecting defense evasion attempts?
Yeah, good question. So the OS itself affords vendors, developers, whomever, the ability to plug in and get, events, telemetry, etc. So defense evasion, if I understand the question correctly, looking at what does the OS emit and what's a baseline default behavior that a typical user would engage in effectively, trying to pair that relationship between the two. That's the best way I can answer anything related to defense evasion, because it just kind of depends, I guess you could say. So.
Ooh, all right, question from Chompy in the room.
Oh, dear Lord.
When do you expect Microsoft will implement the newer mitigations in a major release? For example, the previous mode mitigation has existed for over a year in preview, but wasn't implemented in the 23 H2 release.
Yeah, I was just going to say, I submitted my slides right before 23 H2 came out. So I was like, oh, goodness, I said insider preview. And yeah, so it's not there. That's a good question. A lot of these things are gated by feature flags, as we saw in there. It's hard to say. I don't know why, but I look at it from the perspective of Dave Wesson, for instance, talked about how the Microsoft ecosystem has 10 million source files across the Microsoft ecosystem. So the best answer I could say, I guess, if I'm trying to be as correct as I can be, is maybe there's some issue related to some unforeseen thing that's arisen that we're just not aware of. That's really the only thing that I can think of, because the mitigation itself seems pretty straightforward. So that's the only thing that I can conceptualize effectively. So
Another one DM to me. Do the old how dispatch table overwrite techniques still work?
yes and no. So they work from the perspective of, like, if you do it, and this sounds like a really weird way to answer. If you do it, it will work. But there's an issue with patch guard, for instance, that monitors some of those dispatch tables. And also now you have kernel control flow guard. So it won't work when that's enabled, but the issue is you have to have HVCI enabled for kernel control flow guard to be fully implemented. So as of right now with HAL dispatch table, the only thing you couldn't do with HVCI disabled is overwrite HAL dispatch table with a user mode address, because there's something called software SMEP. It's a type of software SMEP that effectively says, hey, I see you're putting a user mode address at HAL dispatch table. That should never happen when we go through the KCFG dispatch logic, but it won't enforce kernel control flow guard. So if you override it with a kernel address, for instance, without HVCI enabled, that should still work.
Yeah, HVCI is a nasty one.
Yeah.
Okay. So question from in the room with Ron here. Are these mitigations in the previews implemented automatically, or do some of them require client software to be updated or recompiled?
So it varies. Some of them are compile time controls like control flow guard, extended control flow guard. Some of them are enabled through the exploit protection UI in Windows or documented API calls. Some of them are just enabled by default and are there. So they're kind of all over the place, and the documentation isn't necessarily the best. A good example is kernel CET just recently got a UI toggle. So before that, it was like an undocumented registry key. Then it was a group policy object you could tap into. Now it's a UI toggle. So they're kind of all over the place, depending on what the mitigation itself is.
Nice. This question, I'm trying to figure out what it is asking. What are specific tools? I think it is asking for taking a token. Like, is there a way, automated ways to do it? I'm not quite sure.
Like automated token stealing?
I think so.
It depends. I'm sure that there's some exploit kits out there that can automate that process. The only thing you would have to worry about is process object, eProcess, and the executive is undocumented, the actual fields, it's opaque. So you have the issue with the offset of the token changing across various versions of Windows. But I'm sure that there's some exploit kit out there that compensates for all of that and can automate it and hot swap them back and forth as well.
Great. There's a question from Laura. If you could elaborate on that question a bit, and Connor, I'm sure can answer it in Discord, but I'm not quite sure what to ask there. One last question we got time for, that is, hello, Connor. What do you think about control flow enforcement technology? Would there be a possible idea on a bypass? So
yeah, so there are some, a lot of them are academic papers. I think there was one blog recently by Offensive Security related to it. There's something called counterfeit object-oriented programming, where you effectively just use code reuse, but don't overwrite return addresses on the stack. There are some issues where, like, the import address table, for instance, is like a trusted region where you could overwrite the import address table even with HVCI enabled and do a function call instead of a return. But from the perspective of what could you do with return addresses, that's effectively mitigated because it's a hardware mitigation if you're specifically trying to use ROP and not mess with it any differently.
well, I said one last one, but this is a really cool question that just came in. What are your thoughts? Do you think that Microsoft will ever rewrite the entire operating system in Rust?
Thank you for that question. I don't know about the whole OS in Rust, maybe eventually, but what people I think miss a lot of the time is just how much legacy code is there. And, you know, we can sit here and say, oh, well, they should redo it in Rust. That's a huge feat. Now, I'm not saying that, oh, it's too difficult, so we shouldn't do it. They're already starting to do a little bit with it in Win32K, if I believe. So targeting some of the more popular attack surfaces. Maybe we see it in the future, but myself, I like C too much. So yeah, that's what I would say about that.
Cool. All right, round of applause for Connor. Great talk. And great questions too.